Today we're going to continue our session. Okay, we have covered the chart work and also the sailing. And today I'm going to talk on geodesy, datum, projection, and coordinate system in navigation. And for starting from next week, Dr. Aimi will take over the class and we'll finish as soon as we can this part. Okay, for this case, geodesy, we start again, is one of the oldest profession of the world, okay? And it comes from the word geo, earth, and dicea, divide. Geodicea, dividing the earth. So it's a combination of these two words. Very simple, very straightforward. And then definition of geodesy. Okay, the science basically is things that you want to measure. The geo, okay, the world, you want to portray how the earth, how do you want to measure the earth's surface. And as long as you can represent the earth including the gravity field, that is what it meant by the geodesy. Okay, and then how do we define the shape of the earth? Because we know that, do we think the earth as a sphere or flat? Okay, this comes to the some people who in some kind of group who thinks about the theory of flat earth. If you have any comments, you can also leave comment. What do you think about the flat earth? But it's actually a spheroid when you look it from the outer space, slightly larger in radius at the equator, okay, at the middle part here, slightly. I can use some here, laser pointer, yes. So slightly larger in the equator, and rather than the pole, because when it's spinning, it get bulger in the middle, jadi besar sikit in the middle because of the mass, and also because this is the part C, the axis where it turning, spinning. Okay, as we know, Earth is not a sphere and it's not distributed uniformly because of the mass. Because the land mass is different from the sea, so the gravitational pull is not uniform. Okay, as I said before, due to the rotation, equator tu slightly bulge. Tengah tu dia bulge sikit. And post slightly flatten. And the terrain is not uniform. Ada banyak bentuk muka bumi that is not uniform. Okay? The highest spot on Earth, because of this bulge and terrain yang not uniform ni, we have a different height of peak around, scattered around the Earth. So one of them is Mount Everest, 850 meters above mean sea level. So this is very important, this statement, above mean sea level. And what does it mean? Kita akan tengok lagi. The highest spot pula, yang mana dia closer to the outer space, is Mount Chimborazo dekat Andes. 6,100 meters above mean sea level, which is slightly, you know, Mount Everest lagi high, lower, tapi the sitting on a bulge make it 2,400 meter taller than the Everest. Maybe from the point of view of the mean sea level, it is slightly lower, but because it's sitting on the bulge, make it from the center of the Earth, dia adalah lagi closest to the outer space. Okay, so if you look at this part, you can see highest altitude dia measured from the sea level, 8,000 meter. But the tallest mountain from base to peak is Mauna Kea. From base to peak, dia macam the tip of the iceberg. You can only see the tip here. But if you really measure from the base, it's actually ini higher than the Mount Everest. And you can see here, because of the Mount Chimborazo ni, located at the bulge. From the if you look from the center to the highest peak, it's actually lagi tinggi from the Mount Everest. But because Mount Everest located somewhere at the lowest point of the bulge, flattened point, so that's why we count it from the mean sea level. So what I want to say is that the measuring base point kat mana start, and that's determine the differences between your measurement. Zero to start from where? Because Earth ni shape dia tak sama. So where do you find your base, your first zero point tu? Because when you shift the 0 point, all the other value akan berubah. Okay, shape of the earth. Okay, kita ada untuk street plan. Okay, sekejap saya okay. Untuk street planning, kita tengok orang kat tepi-tepi buat engineering survey. We consider the earth as flat, as one straight line. Okay, and then we want to do a geography, small scale mapping, survey calculation. We consider the shape of the earth as sphere. Not consider, we assume it. It's because in order for us to do a simple calculation, we make assumption. But we want to do accurate mapping, we use ellipsoid. And then we include the heighting. We use the geoid assumption. Okay. This is the simple representation of the Earth. Mean sea level is a surface of constant gravitational potential called the geoid. Okay. This, you can see the red line here is the geoid. It is the Earth's surface. Earth's surface is not uniform. You see, it's not uniform with all the height and terrain. So sea surface is here. So this is the starting point of the mean sea level. Ellipsoid, the one that disregard the topography height, and geoid dia consider the topography height juga with gravitational potential. The key differences between ellipsoid and geoid. What are the key? Okay, geographic coordinate, latitude and longitude. Kita tengok. Latitude, kita belajar dah. Longitude defined using ellipsoid. And ellipsoid ni rotate around the axis tu. Elevation defined using geoid. Elevation, tinggi. Surface of constant gravitational potential. Earth datums define standard baseline value of the ellipsoid and geoid. More on this later. And usually used in general purpose atlas and maps and textbook. Okay, so geoid ni dia ada gravitational surface of equal potential which approximate mean sea level. Dia macam mean sea level tu, because of this equipotential surface, dia akan static at one level. That determines the mean sea level. Macam air tu, you goncang macam mana pun, at one point dia akan mencapai dia punya equilibrium point lah, equipotential surface dia panggil. And that approximate the mean sea level. Okay, because of the shape of the geoid, they're not smooth and regular because there ada banyak density variation. Ada banyak, sini ada land, sini ada land, sini ada sea. So when there's a difference in land masses, sea, salt, ada air masin, air tawar, density berbeza. So bila ada density berbeza, dia punya surface pun berbeza. It's not completely round or sphere. see here from the World Geodetic System, 84 geode heights. Okay, you see different heights around the world to 70 meters up to minus and 100 meters. Okay, I'm sorry, it's keep popping out. Popping. Okay, so what we need to do when we want to consider this system measurement, there's a lot of irregularities. Some irregularities can be ignored. Okay, for example, terrain, walaupun dia important locally, it can be it's not going to be ignored. You can assume it as a flat first. And some depth, you can it's too deep. Sometimes you can just your measurement, you can first ignore it for the sake of the simplicity of your measurement. Okay, why do we need ellipsoid? Ellipsoid ni without the height lah, terrain. Okay, the image here depicts the Earth shape without water and clouds. Okay, it looked like a sloppily peeled potato, not a smoothly shaped ellipsoid. Ya, buang air, buang ni. Tapi ni this is the land mass, and this is the rest is full of deep deep ocean semua tu. Calculation of geographic position is very complex. You nak kira macam mana? Where is the center? Sini ke center dia? Sini ke center dia? Sini ke center dia? You never know the correct center. Maybe you say kat sini, tapi when you zoom in, dia lari dah berapa meter. So this simplified mathematical surface is an ellipsoid. Sini, this part. Okay. So tadi surface tadi kita buang. So the geoid and two ellipsoid. You can see this is how they want to fit it. This is a geoid, and then kita nak fit two ellipsoid dalam geoid tu. Ada one and two. Okay. And because ellipsoid ni dia tak sama dekat different area, this A and B can be changed accordingly. Because we know when they rotate kat sini become a bit bulgier. So A lagi tinggi. And kita boleh kira dia punya flattening ratio dia. So why kita nak use different ellipsoid? Because the Earth surface tu is not symmetrical. So ada certain place yang boleh fit some ellipsoid, there's certain area cannot fit. And that is the reason why there's a need a different ellipsoid. And then we have a lot of center point. And then this center point ni lah we need to somehow connect it together in order to get the standard point yang can represent all. Okay. We know that the spheroid the slightly different region of the Earth. Okay. So ada banyak measurement at regional scale. Everest, this is different. And then you have the WGS 84, the GPS worldwide. You have Clark 1866. So the one that you've been using now is the World Geodetic System. This one is standard one worldwide. But before that, there's a Clark GRS International one vessel. Even China and Japan, they use their own geodetic system because for them maybe the standard one cannot represent the the topography very well, so they need their own system. Okay, because of that, there's a lot of ellipsoid, many datums because everyone using different reference point, different origin, orientation of axis, different shapes and sizes, different geodetic result too. The geodetic datum is the location, the orientation, the shape, the size. What do you use? The ellipsoid the- in space to making sure we are where we think we are. Because if some other place you use different ellipsoid, different datums, and then you give the coordinate to the other people at other part of the world, and then they put that coordinate, and then it's end up it's not exactly we think we are because both of you using different reference. Okay, so I'm not going to explain about this. Basically, just show you the geographic latitude and longitude, and then also the ellipsoidal height from the supposed center. Okay, and when you have different geodetic datums, you will have your own latitude, your own longitude. That is something that we know lah, because the base is different. You have two. Okay,